Yeah. Ja. Ja. Okay. Dann, ich frage jetzt einfach mal nach, ob wir nicht auch Tische mitbringen können.
Yes. So good evening to this week 7 session of electrical measurement and electronic instruments. So I think
Ja.
okay, we'll start with today. We'll
Okay, dann.
let others also enter by the time. So yeah, so
Also
in
vor
last week
Ort
we saw
bin ich
we
wahrscheinlich
saw about
auch
these
erst so zwischen 6
potential
und 7.
transformers, current transformers, and then we also saw like some flip-flop questions.
Ja, also wir
And
sind auch
in this week,
morgens sind noch ein paar
in
Leute, die halt schon
lectures,
Sachen rüberräumen.
so
Die
you
sind
were
noch
being
auf
introduced with this
Unterwegs,
operational amplifiers,
da.
like how
Das
what are the ideal
schon,
characteristics
also
of an
selber
operational
ein bisschen
amplifier,
Kabel über muss.
and then you were also being told about the
Und
difference between inverting and non-inverting of op-amps,
Ja.
and then how they differ from Smith triggers, which are not like generally they are comparators. Today we'll be solving some of the flip-flop questions as well as some op-amps questions. I will be going through some data sheets of operational amplifiers, so as to inform you about this, how we can use this ICs, which like ICs integrated circuits,
Ja.
where these op-amps are. So how we can use op-amps in practical applications.
Also
So
dann
we will be
frage
going
ich da
through
auch
that
nochmal
also.
nach.
So
Und
before starting with the extra questions and all, I will be
Frag
going
jetzt
through the
noch
assignment questions, which
ja,
will
erstmal
help
die,
you
ob die
in
noch
this
irgendwo was herkriegen können.
this week's
Aber,
assignment. So this was previous
die
years.
selber
These
kommen.
were
Aber ich
previous
würde
year
sagen,
questions.
wir machen das natürlich jetzt über Sie,
So
wenn die das nicht haben.
yeah.
Und das mit dem Pavillon machen
So
wir
first
dann
question
die
says that so we have to find. I think most of the question we have to find the output voltage of these op-amps.
Ja.
So let's see how we'll solve those. So we were being we were being taught this virtual short and all those ideal characteristics of the op-amp. So we will be using that while using these questions. So let's see the first question. So we have. So the question is saying we have to find this V naught output voltage.
Hallo, hier ist Daniel.
So we have 3 volt and 2 volts supply, and we have these two resistors. So so let's say first of all we'll have to see whether the circuit is in negative feedback or positive feedback. So if the circuit is in negative feedback, then we can apply those ideal characteristics, that virtual short. But if that is in positive feedback, then things will change. So but here in this case we can see this is a negative feedback op amp. So that is fine. One thing is fine, so we can apply that virtual short. So if this is in negative feedback, so this is 0 volts, so this can also be 0 volts. So by using nodal equations, or even using like voltage to current transformations, or like directly applying the inverting or non-inverting formulas, we can go with this. We can get the V naught value, but I will go with this like simply going with this nodal equation, so that it will give you more understanding and you can solve any type of question. You don't have to remember that inverting and non-inverting conditions of the formulas of the op-amp. So in this case, like we will have let's say, so this is our node. If we apply this nodal equation here, so then it will be 0 minus 3,
Ja,
this branch, this branch, and we have this branch. So one thing to keep in mind, like in this branch there will be no current, and in this branch there will be no current, because we are assuming these are ideal op-amps. So we will have, if we consider this as node, so one current will be here, another one will be here, and another one will be through this at the output, and it will come close it paths from this side. Okay, so just apply this. So this will be first branch, then we have the second branch, it will be 3k, plus we will have then this feedback branch, so it will be 0 minus v naught by 2. So if we solve this, we will get minus 3 by 4 minus 2 by 3 equals to v naught by 2. So this will be 9. How much this will be? This is 9. This is 8. This will be 17. 4 is 12. Just let me know if I'm doing some mistake or not. So this will be 6 2
Ja, vielen Dank, dass Sie mir wieder geholfen haben.
17.
Ja, aber Sie sind auf jeden Fall deutlich besser angekommen telefonisch als ich.
So we'll get negative of minus 2.8 volts, something like that. So simple. We use this nodal equation, and we don't have to remember like this inverting, non-inverting conditions and all those things, and we'll get to our solution. So I think this is simple. Another approach can be to solve these questions, so you have this thing, but that may be a little lengthy, but it may help in some of the cases. Like you can see this, so you can convert this into current and source, and this branch also will be converted into, so this is ground, so this is basically, so we will have this 3 kilo ohm resistance here. This is 4 kilo ohm, and this current source will be 3 by 4 milli, like kilo we can say, and this will be 2 by 3 kilo. So you can add these two current registers, and then again you can transform them back to voltage, and so again you can do this voltage and resistance. So this two branch will be reduced to one branch. So you can go by that approach also. It's up to you, like whichever you prefer. So, but I think nodal equations for currents are fine for that, like solving these kind of questions. So yeah, so first was this. So I think most of the questions will be based on this only. So let's see the second question. So we have this, so now we have 2 volts here. Now we have 2 volts in the negative feedback. So first of all, just keep in mind whether that is a positive feedback or negative feedback op amp. So here in this case, we are giving it a feedback from negative terminal. So it's a negative feedback op amp. So this condition is fine. So then we can apply this virtual short concept. So in this case, we have this 2 volts here. So this 2 volts will be here also. Okay. So if we see this branch, so how this will be looking. So we have something like this. So this is V0. This was 2K. This one. Then we have 4K. We have ground here. This was 2 volt in the negative feedback, and this is because of the virtual short. So if we solve this branch, then the voltage we will get here, let's say it is VA. So VA will be what? It will be 0 volts. Okay, because this is having opposite polarity voltage sources facing each other. So we will have ultimately VA 0 volt here at this node. So if VA is 0, this is also ground potential. So then the current to this branch will be what? 0. Okay, and this same current is going from this branch. Why? Because no current can go from this branch. Why? So let's say this was I current here. This was I, and this will also be I, because here I will not be there. It will not be flowing from this branch because there is no current which is get inputted into the negative or the positive terminal of the op amp. That is the ideal characteristics of the op amp which we learned in the lectures. So that's why this I will be same flowing in this branch. So if VA is 0, this was VA. If VA is 0, then I will be 0. So V0 will be what? V0 will be also 0. Okay, because there will be no voltage drop across this 2 kilo ohm resistance. This also fine. Now moving to the next question. Again we have to find the output voltage of this op amp. So in this case, first of all, just again check whether this is a positive or negative feedback. So see, we have this negative here. So this is a negative feedback. So okay, negative feedback, fine. We can go for that virtual short conditions. So we have 2 volt here. There also it will be 2 volts. Then since this is shorted, so this will be 2 volt. So now we can easily find the I here. This I, and this I will be here in this case also, because here I will not be there. because it is the terminal which is going into the op amp, and that in ideal characteristics we will not have any current flowing inside the op amp. So I, this is here, so this I will be what, I will be 2 by 4 kilo, that will be zero point 0.5 milli. Okay, and this is v naught, we wanted to calculate v naught only, so v naught minus this, so in this branch if we solve for, so v naught minus 2, this is this voltage divided by the resistance 5k is the current for this branch. So v naught will be what, I into 5k, and we have I as 0.5 milli into 5k plus 2 from this side, so v naught will be this. Okay, so this will be how much, 2.5, 4.5 I think, yeah, 4.5 volts. So this will be 4.5 volts. Okay, so I think this is also easy. Also we will not go for this, we without considering this branch we can get to the answer, because this v naught is being like is being seen here also, v naught at this branch, so that is fine. Then moving to the next question. Now again, first of all, see this whether this is a positive or negative feedback. Now interesting thing in this, it will be like I'll tell you. So first of all, this is the feedback is from negative, so it is a negative feedback op amp, one condition. Okay, then the second thing, just observe this part of this op amp. Now if I draw this separately, forget about what is attached here. So this is basically a voltage source with a resistance, you can solve. But what I want to tell you that, so this acts as a, so let's say there was some resistance here and some voltage, whatever it was. So this is basically a unity gain amplifier. So this is a term used to define such kind of op amps where the feedback loop is having no resistance, or like or basically we can say the gain will be whatever the input we are applying, the output will get the same. So if we have something like this, so we had something like, let's say this was the voltage source, and we simply connected the negative terminal of the op amp to the output of this op amp. So then what will happen, whatever v1 is there, because of virtual short, v1 will occur here, and then v0 will be equal to v1. So whatever input we are giving, we will get that as same as that as the output. Now you will say like, what is the use of the circuit? We are not getting any amplification or nothing we are getting. But these circuits are also called as buffer circuits. So buffer circuits, why? So you must have heard of transformers, and I think, yeah, in machines fun you have been taught about that transformers things. Now in transformers, one of the important applications of transformers is that they act as an isolating circuits. So what happens, like if we have some, we saw that in this potential transformers and current transformers also, when we have a main line, so we are attaching some transformer across this, so what is happening, it is disconnecting the main, so this was your main circuit or something, and this was your supply line. So this is very high voltage, and like a lot of current is going from there, or it's very high voltage. So what will happen, this act as an isolation. So why? Because there is an air gap there, so magnetically it is coupling the supply line to the main circuit. So electrically it is disconnecting that, but still we have all the effect of this circuit here. So electrically we disconnected that, that's why this is an isolation circuit. So this same thing can be done by this op amp, which in buffer in this voltage this unity gain amplifier, or we can say buffer circuit. Why? Because all the supply was here. Okay, so we are not directly connecting v0 with v1, but instead, because of this virtual short concept, we are using that concept for isolating this supply volt. This is supply line. Now you can say, okay, this is supply line or something, supply thing, and this was where your main circuit was. Okay, so we disconnected electrically. We didn't connect that electrically, but due to this virtual short, this V1 is being shown at the output. So V not equals to V1. That is, so that's why we have isolated this input supply from the output, but still we are getting the same thing where what we were having in the input side. So that's why these are good for isolation circuits. So this buffer circuits, or this we also call them as isolation circuits in electronics, because we cannot use transformers everywhere when we have like ICs of like tip of your finger, tip of your like your finger. So it's that small that ICs are, so we cannot use transformers there to isolate our circuit from the main supply. So that's why we go for these circuits. So that's why this is a very important circuit in electronics. Okay, theory apart, now the question. So the question says, so we had, so now, so but the question is simple only. So now I will just, for clarity, so now we had negative feedback, we have this normally attached here. So let's say we have some v, so what if, so what will be the voltage here? So if we use the concept of virtual short, then v naught is being reflected here because there is no resistor there, so that v naught will be reflected here also, okay, because of virtual short. So then we will have, again now we can simply use nodal. So there is no current here, no current here, only one current is there, another current is there, so we'll only use nodal there. So this will be v naught minus 4 by 4k plus
Hallo,
v naught minus
jetzt Daniel
2
nochmal.
by 4k,
Eine
which
andere
will be
Sache
equal to
noch.
0.
Ich
So if you
sage
solve
aus,
for v
hätte schon
naught,
damit angefangen,
then we'll get
aber wäre es möglich von einem
v naught equals to 3 volt.
insgesamt zwei
Okay,
Packungsweise für den
so now that question becomes simple if you know this virtual short and all those things. So
okay, ja,
this is also fine. Now the next question. So now the next question says, again first check whether that is like a positive or negative feedback. So in this case again we have this negative feedback thing.
Yeah.
So we can apply simply that virtual short. So this is 1 volt here. Here also it will be 1 volt.
Ja, nee, also,
so we have 1 volt here
sagen,
in this case. So now we have to calculate V naught. Okay. Again, simply using, let's say, so this I current will be same in this branch. So we will have 1 minus 4 by 2k is the current. So since we thought this will be the current direction and it is coming out to be negative 2 milli, that means current will be going up actually. Okay. So now we will have V naught. So in this branch we will have V naught minus 1 by 4k equals to what? Minus 2 milli, because the current direction was opposite. Okay, so we will have, so to the 8 this is, oh sorry, this is minus 3 by 2.
Okay. Vielen lieben Dank.
This one.
Tschüss.
This is minus 3 by 2. Yeah. So now this will be minus 3 by 2. So V naught minus 1, it will be into 4 to V naught will be minus 5 volts. Okay. So we will get this. V naught equals to minus 5 volts. So simple. Once you apply the ideal characteristics of the op-amp, you have to simply use any basic circuit analysis technique and then solve the questions. So this is, I think, also fine for you. Now the next question. So it says again we have to find this V naught voltage, and that will be, so 1 volt we have. So first again we have this negative feedback. Fine, we have 1 volt here, so it will be coming here simply 1 volt. So now, so since this was 3 volts there, okay, so V naught minus 3 equal to 1. So I'm using nodal here, KVL here. So V naught, some drop in voltage because of this battery, that is minus 3, and which is equal to this 1 voltage, 1 volt voltage. So we will have in total of 4 volts. Okay. Again simple. Or yeah, so you cannot so you can use nodal layer, but then there's a concept of super node here. But instead of that, we can use simply KVL layer without using super node concept. It will make things unnecessarily complicated. So this is also fine. So if you have any doubts, so you can ask me or you can interrupt me in between. So now the next question. So they are saying this is a two input amplifier. So we okay, they have two inputs here, and we have, so again we have to find the output voltage V naught. So okay, so again that check whether this is a negative feedback or not. So we have this negative feedback here. So I think positive, although connected, but negative feedback is like dominating in this case, like this. So we can use this concept of virtual short here. So let's say this voltage will be we can say V negative, we can say this. So this, because of virtual short, this will be V negative. Okay, now uh, we have V negative and this is 4 volts, so it is mentioned here 4 volts. So we can, so now if we use nodal here in this case, so I is not going inside the positive terminal or the non-inverting terminal of the op amp. So we can simply use a nodal here, that will be V minus minus 3 by 1k plus V minus minus 4 by 4k equals to 0. So if you solve this, then 4V minus minus 3 into 4 plus V minus minus 4 equals to 0. This will be 5V minus 4 plus 12, 16 by 5V minus. So we have V minus here. Now so we got this voltage V minus. So if we are able to get this current, let's say this was I2, this was I1, so this is I2 current, and this current same will be going through this branch because no current will be going through this branch, so it will be straight away going to the output. So what will be I2? I2 will be, so I2 will be 4. So simply using this branch, 4 minus V minus divided by 4k, it will be 4 minus 16 by 5 divided by 4k. Okay, so this will be 4 by 5 into 4k.
Okay.
This one will be this, then it will be 1 by 5 milliamps. So we know I2 is this current, we know the value of I2. Now simply in this branch, the feedback branch, you can use this. So then we will have V minus minus V naught divided by the resistance, that is 4k here, equals to I2, because that is the current flowing through that. So V minus we know 16 by 5 minus V naught we don't know, I2 we know, so 4k by 5 milli, this will be cancelled out. So 16 by 5 minus 4 by 5 equals to V naught. So we will get 12 by 5, so 124, 2.4 volt V naught. Okay, so this will be the answer. So V naught will be 2.4 volts. Fine. Again easy, no difficulties. You should not face any difficulties in this. Now the next question. So now again negative or positive feedback. So this is a negative feedback. So we have this negative feedback, and then in this case this is kind of an inverting amplifier, because we have this source at the inverting side of the op amp. So this is 0 volt. Simply again we'll go with that, we have to find V naught. So 0 volt here, that is grounded, so virtual short, so we'll get 0 volt here. So if we have to calculate the current in this branch, let's say this is I, so I will be what, this 1 volt minus 0 volts divided by 4k. So we'll get what? 1 by 4 milliamps. So we have the I current, and this I current will be flowing in the feedback also. Why? Because no current is flowing into the inverting side of the op amp. These are ideal op amps. So we will have so we can use KVL from this node. So 0 minus, so this is like going in increasing potential of the battery. So we will have plus 4 volts, then we will have minus, so this is dropping here, the voltage is dropping, this is plus minus. So whatever conventions you use, you can use accordingly. I use this convention. So this will be a drop voltage across resistance, so this will be 8k into I is 1 by 4 milli. Then we have this final voltage which is equals to V naught. Okay, so this will be 2, so this will be 2 volts, V naught will be 2 volts. Answer for this, yeah, 2 volts. So I think this is also easy. That same virtual short concept you have to use and then solve the things. Now the next question, ninth question. So now we had this 0 volts here, but instead of that we have this 5 volts here. So I will also help you solve this question with the, now we will not use nodal, we will use the superposition. Let's see how we can use superposition here, just to expand our knowledge base. So superposition, we will be using, if we use one source, we have to, for voltage sources, we have to short circuit all the other sources. If you are using current sources, then we have to open circuit the current sources. I think, yeah, that is the case. So let's say if we use only 2 volts here, so this is, let's say this is 2 volts, so we will have to short circuit this 0, 5 volt is not there, only 2 volt is there, 4 and this can be V01. So what will be V01? So this is this will be inverting amplifier configuration. So what is the formula for that? That is the input voltage, that is 2 in this case, multiplied by the feedback resistance 4k divided by 2k and a minus sign there. Okay, because it is inverting. So we will get minus 4 volts. And now for V02 will be when we are short circuiting the 2 volt supply. So this will be, now we are going with 5 volt supply. So this was first, this we are for second case, for 5 volt supply, 2 kilo, this is 4 kilo, this is V02. So V02 will be, now what is this? This is an non-inverting configuration. So for that we have input voltage is 5 volts and 1 plus the feedback resistance, that is 4k, this one, divided by the input resistance, that is for 2k, this one. So this will be 5, 2, 3, 15 volts. So what will be the total voltage? It will be V01 plus V02. So 15 minus 4, it will be 11 volts. Okay, now this is superposition, is simply the application of, so what is like, what you can see, if another way of seeing this question is, one way is like that nodal which I am solving all the previous questions with. Second was the superposition. Now if you are so much good, now when you will practice and you will become so good in the superposition, then you will simply say, okay, we have a this a supply at the non-inverting side and a supply at the inverting side, and we have some feedback registers and this register. So you can directly say the input will be, that is the V plus, that is the non-inverting side voltage, 1 plus what is the gain from the non-inverting side voltage, that is the non-inverting amplifier gain, which you have learned already. So it is 1 plus RF, that is feedback resistance into R1. R1 is this, plus V negative, and this is the gain because of the inverting terminal, that is this one. So that is V minus, and this will be negative of RF divided by R1. And this is what we got from the superposition also in this case. So you can directly apply this also in this case. So you have RF, you have R1, keeping the conditions of magnitudes and signs, signs in mind. So this negative, so you will get to again 11 volts. Okay, so this is basically the combination of the inverting and non-inverting amplifiers. Okay, so this way also you can approach these questions, but only if you are sure about that. So if you are not sure about, okay, this very complicated circuitry in front of the op amp and in the feedback also, just go with the nodal. You will not face any difficulties. Just go with the nodal. You don't have to remember the main formulas of this inverting non-inverting amplifiers. Okay, but although it may be time consuming, but if you have practiced enough, so it will be fine. You can directly apply the formulas. Okay, now the 10th question.
Yeah.
The question says, again we have to find V naught. Oh, is this? No, it's okay. So this is simply, so we have a negative feedback op amp here, first thing to keep in mind. Then we can apply that virtual short concept. So here we can apply, so let's say this is VA. So, oh, sorry, I will say V minus for simplicity. So this will be V minus.
Yeah.
This will be also V minus then. Okay.
Okay. Good.
And this is like what? Voltage divider thing. So we have a 2 volt supply here. So 4K, 4K. So voltage will be divided equally among them too. So this will be also 2 volts. So we have 2 volt equal to V minus. I think this is fine. Very like easy to understand. So if we have 2 volts here, so this will be 2 volts because of virtual short.
Okay.
Then so if we have, so now we have to find the current I. Okay, and this same I will be flowing from this also. I. Okay. So what will be I? I will be equal to this 1 minus 2 by 3k. So it will be 1 minus 1 by 3k, and the sign itself shows that because this is less voltage and this is high, so current will be in the opposite direction, actual current. So it is minus 1 by 3 milli, but okay, current signs are fine. If we go in this branch, then we will have V minus minus V naught divided by 2k. So we are going for this branch. Okay, so that will be equal to again what? I, and this I is negative because we are considering this side the current direction, but now it's flowing opposite. So this is negative, so we will have minus 2 by 3. So minus V naught plus V minus, I just shifted V minus this side. Now we had V minus as 2 volt, so it will be minus 2 by 3 plus 2. This is 4 by 3 negative V naught. So it will be okay. Did I did something? One mistake. Sorry for that. So this will not be 2 volts. This will not be 2 volts. This will be 1 volts actually, because we have 2 volts. It will be divided into half. So this will be 1 volt. I'll just erase that. Just calculation mistake. No issues here. So we have 1 volt in this case. This will be 1 volt. So if this is 1 volt, so this will be 1 volt also. So this was 1 volt, this was 1 volt, so there will be no current in this because these are same potentials. Current will not flow. So sorry for the inconvenience. I'll just erase these things. Okay, so this is 1 volt. So I is 0. Now I will be equal to 0. Then so if I is 0, then this I will be also 0. So if this is 0, then what will be V naught? If there is no voltage drop, then V naught will be 1 volt. Okay, because this was 1 volt, no voltage drop across this, so we will get V naught equals to V minus, so it will be 1 volt. So just keep in mind like simple things, how to divide the voltage, how to use nodal, how to use KCL, KVL, then superposition you can use. So all are like circuit analysis techniques. Then so if you're well versed or well practiced in these, then you can directly go for these formulas, but I will still recommend practice with the basics. Then we talked about this buffer circuit, that is very important. If you pursue your your like maybe MS or masters or something in electronics, then this will be really helpful for you. Buffer circuit. Okay, so we are done with this assignment questions. Now I will be talking about, so I will be showing you the datasheet of Opamp. So many of you might have not heard what datasheet is, or like what does it conveys. So we will be going through that datasheet. So basically datasheet, like, so I have two datasheets, I will be comparing them. So datasheet basically tells you, it's kind of a manual for these ICs. ICs is this integrated circuits. So this is from Texas Instruments. So this will give you the like the practical idea of how these ICs behave and what are their limitations. So whenever like if you will be working on some project or something, and like if you want to develop something using these ICs, integrated circuits, that is like Opamps or something. Let's say you simply wanted to uh, develop some amplifier circuit. So very basic idea. You had some voltage, and simply you had to like make, let's say, a sound system or something. So you have to amplify that sound. So basically, if we use some transducers or something, we can convert that sound signal into electrical signal. But what if that electrical signal is very less? So we have to amplify that. So you will be using some op amps. And how these op amps can you use? So you can use these op amps using these ICs. So I will show how these look. I have this thing. Wait. So see, if you can see this. So this is how this. So this is this black thing you can see here. So this is the example of LM741. So this is kind of an op amp. So all the circuit is inside this, or made of transistors and all those things. And these pins denote like some. So these each and every pin is having some like you can connect your supplies, your grounds, and your feedbacks based on the information given in that data sheet in these pins. So we will be looking then. So by simply using this simple black small thing, and this is very small, it's like this much small, and you can find in markets even smaller this these packages in like in market. So this is like how you can normally use op amps as. So now we will be seeing, okay, what's there inside and what are these limitation of this op amp. So whatever you learned till now, this op amp thing you were like listening again and again, this is what op amp looks like. Okay, so now, so when I was like telling you about this amplification, so you use this op amp, you use some combination of feedback and the input resistance, and you amplified that input signal. So simply you made an amplifier circuit using op amps for your amplification of your some simple sound signal or something like that. So this is like how you can easily use this op amps for. So but then the question will arise like which op amp to use. So there are n number of op amps in market, like with lot of variations in their like their voltage supplies, their like bias currents, offset voltages, and all those things. So which thing will suit your application the most? So for that you should have the knowledge of these data sheets. Okay, so keeping that in mind, let's see how we can read these data sheets of op amps, operational amplifiers. So this is an example of LM741. So features they provide, okay, this is, so the LM741 is like a very, we can say, kind of one of the earlier op amps which came in market, and but still used, because this is like a kind of a standard. But still we have much better op amps than this. But just for the example, I'm giving you this LM741 example data sheet. So features they said, okay, overload protection and the input and output. So they have this overload protection, so we don't have to go deep into that, how it works, overload protection and all. But then they have this latch up and common mode range. So they have latch up protection also. So these are protections, no need to go inside that. But let's see the applications. So the application, if we see, so the comparators, so they can be used as a comparator. So what is a comparator? You must have read in your lectures. So comparator is basically, so if you have signals, you don't have any negative feedback or positive feedback, but you can have positive feedback. Comparators work in that also. Smith trigger is kind of a comparator. So you have V1 here, you have V2 here. So based on the magnitudes of V1 and V2, if V1 is greater than V2, then the output will be negative saturated, because V1 is at negative, and if V2 is greater than V1, then output will be positive saturated. So this is the example of comparator, like based on these values of V1 and V2, you can get either positive saturation or negative saturation. So these can act in that as a comparator. Then we have multi vibrators. So these are also like I think to switch for like modulating pulse or something. For that, multi vibrators are used. Like so, like there are many like applications for this also. Then we have DC amplifiers, so like amplifying a DC signal or something, simply to make 2 volts to 4 volts or 2 volts to 6 volts. Then we have summing amplifiers. So if you have two voltages, we so if you had, like, let's say you had two supplies. So basically, if you have two supply V1 and you have V2, so how you can add them and to get V1 plus V2. So you can get that, you can do that with this operational amplifiers also, like, so this LM741 can do that also. Then integrators and differentiators. So if you want to integrate some input, so let's say you had this what you said, this sinusoidal voltage. So if you integrate that, then you will get a cosine wave, okay, that is phase shifted by 90 degree. Okay, that is what integration means. So if you have this square wave input, if you integrate that, then you will get this triangular wave output. So I think those are used for like lot of applications. So for that, integrators can be used with these op-amps. Then you have differentiators, like again, if you have to differentiate some input signal. So if you had this triangular wave, you differentiate it, you get a square wave, and you can use the square wave for like for a clock signal to any circuit or something like that. So there can be very lot of examples with this. So maybe that's why one of the reasons to name these kind of ICs are like operational amplifiers. Why we name them? Because operational. So these are basically mathematical operations which can be done by these op-amps. So we can do sums from this. We can do like subtractions from this of our voltage signals. We can do integration. We can do then differentiation, and then like so these are the basic mathematical things which we can do, and all we can do with the different configurations of our feedback registers elements, and yeah, using different configurations of feedback in this op-amp, we can use all these applications. Then we have active filters. So active filters, basically you have heard of this capacitor and resistor in series. So that act as a, I think, like this. So this is what. So if you give a low input signal, low frequency signal, this will not pass, because capacitor will not be passing a low frequency signal. It will be acting as a like it will be acting as a high impedance element. Okay. So this is basically a high pass filter, and we have this low pass filter also. So if we have this if we have a low pass signal, then what will happen, like then this input will be what open. So whatever input we will be getting, we will get this as output for low input signals. And for high input signals, for high frequency, high input frequency signals, this will be acting as a short. Okay, so we'll not be getting any output. So this is a low pass filter. So you might have heard about this in your previous courses of these applications of network analysis and all those things. Then so using op-amps also, we can actually have this active filters things. We can like go for these active filters. So this is another example of op-amps. So let's see. So what's written there? So they are saying this LM741 series is a general purpose operational amplifier. Okay. So they have this overload protection, input and output, no latch up. Okay. So see,
Da kann man halt auch
typical
hingehen, wenn es mal so ein bisschen
application, they
laut ist, dann
can
halt den
say
anderen
this
Regeln und
as,
da ein
so
bisschen
you
entspannter
have seen this. So
weil
this
nach
is a
10 dB
non-inverting
dann
amplifier.
Lautstärke maximal draußen sein wird. Also das wäre eigentlich.
Non-inverting amplifier. Okay. So you give input at the non-inverting side and you
Okay,
will get
dann
output as V
frage ich ihn
input
mal.
1 plus R2 by R1. But okay, you saw this thing here.
Das
Like
hatte
okay,
ich
you
auch
can
nicht
draw this
auf
circuit.
dem
Okay, this
Schirm,
is a
weil auf
non-inverting
der Rechnung halt
amplifier.
nur steht
But what will
Service-Kräfte
happen
was das
if you
ergibt,
will,
aber
if
das
you
hat
actually
irgendwie
want to
gerade
do the
nichts
connections
antwortet
like with
bekommen.
wires and all? So
Deswegen
how
würde
you will
ich
be
jetzt
doing that? How you will be
folgendes.
realizing this non-inverting amplifier using that black IC which I showed you? So let's see the pin layout of this. So this is very important.
Okay.
In a data
Gut,
sheet,
vielen Dank.
when you go for any data sheet of any IC, this is very important. So this shows that which pin. So you saw this thing here. So these like you can see this for this
Ja,
silver color pointed
das
pins.
bitte.
So this each and every pin is having its own importance and how and what their function is. So let's see. So we had something like this.
Genau.
Okay, so this was that black thing which I just showed you. This is an IC. So you have four legs here and the four legs in the rear side of
Ja.
that IC. So this is an IC
Gut.
and this, let's say this
Vielen
is
Dank. Tschüss.
741 LM74 IC. So this is 1, this is 2, this is 3, 4. So you can say 1, 2, 3, 4. Now you are seeing the top view of that IC, this IC. Okay. So this notch is very important. This notch you can see, I think maybe in this diagram also. So yeah, you can see this notch here. Okay. You can see my pointer, that blue color one. So this is a notch. This is a notch, very important. This shows from where this IC spins are starting. So if this notch is there, so from the left side of that notch, the left side of the notch, that will be the first pin. So this pin, this pin will be 1, then the second pin will be 2. Just follow my blue this thing, blue pointer. Okay, so this is the second pin, then we have third pin, then we have fourth pin, then after that fifth pin will be this pin. Okay, this is the fifth pin, then 6, 7, 8, like that, so on. Same thing we are looking from the top. So we have this notch here. So this notch is very important in order to say which is the first pin starting from. So many times it happened that what happens, like if you are like if you don't know where the notch is or you wrongly misinterpreted the notch position, then you can connect your supply from here or something like that, and you can damage your IC also. So that you have to keep in mind. So let's see what first pin tells about this IC. So first pin says this is offset null. So I will tell you what is offset, don't worry. So this is inverting input. So this is the inverting input. That means you can see this diagram. This is more clear, more better view of that. So this is basically inside this pin. So the second pin is the inverting input. So if you want to use this application, so inverting input is this. Okay, so if you, let's say you wanted to realize this non-inverting amplifier, you wanted to realize using this LM741. So this R1 resistor you had in your hand, and from where you will connect. So this is with which pin? Let's see. So this negative inverting pin is this second pin. So this will be going, so I will draw here only. So we have this R1 resistor, we will attach this to one first pin. So this was one pin. Oh, sorry, second. So this is the second pin, inverting input. So we gave that R1 into the inverting side of the terminal, and then we have this third pin as the non-inverting input. So where we will be giving a supply to. So for a non-inverting amplifier, we have to connect that supply the sinusoidal voltage at the non-inverting side of the op-amp. So that is there, but where? So this will be at the third pin. So this is the third pin, this plus sign. Okay, now we have a feedback also, a feedback resistor also. Let's say this is RF. So this one pin will be connected to the second. So this one terminal of this RF will be connected to the inverting side of this op amp. That is fine. But the second terminal of this feedback resistance is connected to the output. So which is the output pin? So according to this configuration, we have output at 6. So you have 6 here. So now I will give more clarity by drawing here itself. So we gave register R1 here and we connected ground there. Now you will be getting more about this. So after that, so we have this non and inverting input. We gave our supply there. So this is V1. Okay, we connected that at third input. Now we have this output. So from this R1 register, that is the input, this R1, we are giving an feedback register RF and we are connecting that to the output, this pin, sixth output. So this is V0. So you are you imagining when you have this IC black, this black structure kind of stuff. So you connected your R1 at the second terminal, second pin of that structure, and then after that you connected your input, the supply voltage at the third pin of that is this pin. Then you connected a feedback coming over from that IC to the sixth pin, that is V0. So till now this much is fine, but now we have to connect these supplies also, these supplies. So this is V positive supply and V negative supply, where we will be connecting. So you can see this V minus, this is V plus. So V plus is the positive supply. So you will be giving, let's say you had a DC source, you gave from some you had the DC amplifier or like DC source you must have used in your like basic electrical laboratory and all those in your colleges. So this is, let's say this was 5 volts, or let's say it was 10 volts, plus minus 10 volts you gave, and from this also you applied this minus 10 volts, or we can just reverse the polarity to say that this is negative 10 volt. Okay, so this is the supplies, plus and 7. Now this you don't have to, right now you don't have to care about that. Offset null and offset null also you don't have to care about that, but I will be telling you what these offsets are. So but the basic connection to achieve a non-inverting term amplifier, so you have to do something like this. So registers here, input supply here, then output you will get from here, feedback from between 2 and 6 you have to connect a feedback register, and from 7 and 6 you have 7 and 4 you have to supply this positive and negative supplies. That's how you build a non-inverting amplifier. So this is the thing. Now let's go further in this data sheet, what this data sheet is saying. So as I told you, so inverting input, that is the second number. So I am telling you this is the most important thing in a data sheet to look for, this pin diagram. We say pin diagram. Okay, so we had this, we talk about this. So as they said no connect, so we don't have to connect anything at this NC, that is this 8th pin. They are mentioning no connect. Okay, we don't have to connect anything. Then we have this non-inverting input terminal. Fine, we connected that supply, input supply there, and then we have this offset null. I will be telling about that. Then this we had positive supply voltage and negative supply voltage also we connected, and output also we look for. Now let's see what this offset is. So offset is basically, if you had this op-amp and let's say you had this configuration RF, R1, and you had something like this. So based on this circuit, so you will be observing that there is no input supply given to this op amp. So there is no, so this is 0 volts, this is 0 volts, but you will be, or we can say, yeah, so you will be like but surprised to know that even after giving no supply to this op amp, then also we will be getting some output. Okay, you gave 0 supply, then also you are getting V0 as an output. So what is happening here? So basically that's what the definition of this offset voltage is. So in case of 0 supply, input supply, then also the output which you get, that is because of the offset voltage. So you till now you only considered this ideal op amps which had this no current in this branch, like nothing there. And then you had this virtual shard and all those things. Although virtual shard is still there, but in practical op-amps, what happens? In practical op-amps, so we have a voltage like this here. Okay, so this is the offset voltage, and this is because of the internal impracticalities of this op-amp. So this op-amp is still, it's what, it's a combination of a lot of transistors. Inside this op-amp there are a lot of transistors, a lot of resistors being used, a lot of bias techniques are being used. So that cannot be ideal. So that's why this offset, the voltage offset comes into picture. So although we don't have anything in like any voltage supply in this case, but because of this offset voltage we get some V naught there. So that's what they tell this offset as. But then there are many techniques to nullify this offset, because when you are going for like applications in biomedical field where you actually have to consider about even a millivolt of signal, you cannot like play with even a milli or like microvolt signals. So in that case you have to nullify this offset voltage. For that there are many techniques. One technique is to like attach a resistor at a non-inverting terminal, but no, I will not go deeper into that. But one technique is that. So that's why they said, like, if you want to nullify this offset voltage, simply to say, then these are the pins 1 and 5 you have to use. So some elements you will have to attach in between those pins in order to nullify this offset voltage. So that's what they are saying. Offset null pin is used to eliminate the offset voltage and balance the input voltages. Okay. And then in, so this was one ideality, non-ideality in op-amps. Another non-ideality is that, so let's say this was minus plus. So till now I was considering there is no current entering, but there is this IB minus and we have IB plus. So these are bias currents flowing into the inverting and non-inverting terminals of the op-amps. So these are the non-idealities in a op-amp. But for time being we are not considering them, and I think it's out of scope for this maybe course. I don't know, maybe in week a 9 or 10 you may get to know about this. But for time being you just want to know, okay, these are the non-idealities, IB minus and IB plus. These are the bias currents going into the op-amp. So what we want ideally these to be zero, but that cannot be possible. So what happens, like, so these companies, Texas Instruments, Analog Devices, all those companies, what they do, they try to come up with so better circuit techniques, so that they can decrease this value or magnitude of this bias currents and as well as the offset voltages, so that they can make this op-amps look moves toward more idealistic op-amp. Okay, so that is one thing. So now let's go further in these data sheet. So these are, let's see, supply voltage. How much supply voltage maximum minimum you can give? You cannot give beyond that. You will damage that IC. So you will get that smell of burning something. So I think you might have burned capacitors in your laboratory. So you will get the chance to burn these ICs maybe in this your third year, if not in analog laboratory or something. So I'll say do burn one, so that you will be knowing, okay, what not to do. Okay, so these are the supply voltage. One is this plus minus 22 volts supply maximum you can give for these variations. If you talk about LM741C, then you can give only plus minus 18. So these are the company variations with this set. So since we are talking about LM741, so this is the plus minus 22 volts which you can give as the supply to that. Okay, so power dissipation, as I told you, yeah, nothing can be idealistic. So we have some power dissipations inside this op-amps. So that is 500 milliwatt. Then differential input voltage. So differential input voltage means this V1 minus V2. Okay, that how much you can give. So this can be only, so the difference can go up to 30 volts. So that means if V1, let's say, is 30, then V2 should be 0. Okay, it cannot go beyond that. And if V1 is 15, then V2 can be minus 15. Okay, so that can be done. But if V1 is 30 and V2 is, let's say, minus 10, then this will damage the not damage, it will like lead, it will make this op-amp go into saturation. That is the gain. But damage will happen if you will give supply voltages beyond this 22 plus minus 22 volt range. Okay. Then we have this input voltage thing, that is plus minus 15 volts. Fine, that what I told this, that is V1 V2 are input only. Differential was basically the difference between the input voltages, the negative and the positive terminal of this op amp. So then we have these operating temperatures, junction temperatures. Okay, that is not that much important for us, for our application, normal applications. Storage temperature also fine. Now this electrostatic discharge. So basically what happens when you are like soldering these ICs or you are handling these ICs. So first of all, these ICs will come in EST protector sheets. What is like, so these are conductive sheets on which these ICs are placed. So if you suddenly, so your human body can acquire a lot of charge while you have read this about in your basic 12th or 11th class or 10th class also. So this charge accumulation can be so higher that it can, once you touch these ICs with your bare hand, it may damage those ICs. So you should be very careful while handling these ICs. So either you use that electrostatic discharge sheets, like there are like proper setups on which you can solder these ICs on. So like you wear a conductive a glove or something, so whatever charge will be there, it will go into the ground, and like if you are soldering the IC, then your IC will be safe from that, all those charge dissipation. So but if without any discharge of your body, this electrostatic discharge, then what will happen, like if you touch that IC, all the charges will be flowing through that IC and it can damage that IC. But still they have like made this IC to be like capable to handle this much of voltage discharge. So but still you should be careful while handling these ICs. Then we have this we talked about this supply voltage. So normally we use plus minus 15 volts as a range, but we can go till plus minus 22 volts. Then temperature, okay, no need to worry about that. So now these are the LM741 electrical characteristics. See, I talked about that input offset voltage. Although it is an non-ideal behavior of an op-amp. See, 5 millivolts is still there, and 5 millivolts. So when you talk about these biomedical signals, which are like in millivolts only, even less than that, and see your offset voltage is also 5 millivolts, then it can create a lot of interference in your output signal. So that's why we cannot use LM741, this IC, for biomedical applications. There are much better ICs than this. We'll see. Then we have this input voltage adjustment range. Okay. So this is the ranges which we can adjust for this to vary this offset voltage. Then we have input offset current. So input offset current. So I talked about this bias current. I'll just draw that here. So this was negative, this was plus. So this will be IB minus, this will be IB plus. So this is the bias current and the bias. So bias current basically is IB minus plus IB plus divided by 2. So this is the like how you get the bias current. And offset current is given by I offset is IB plus minus of IB minus. So this is the offset current. So this is what they are telling. So this is the offset current. So they have, still it is very less, but still it can create lot of issues. So this is 200 nanoampere, 500 nanoampere, but still we need much lesser magnitude of currents for achieving better applications from these op-amps. Then we have this bias current that is in microamperes, that is even larger. Then input resistance. So somebody would have told you that like many of times you have read that we have infinite impedance of this op-amp, but no, it is not. Although it is almost infinite, that is 2 mega ohm, but it is not sufficient to be called as infinite. Okay, but still we are having a very large input impedance, and that is what we need. Input resistance to be very high. Okay. Then we have this input voltage range. And yeah, input voltage range, so that is the input supply which you give to the so this is at the terminals of this, so these two terminals, so this much you can give plus minus 13 volts. So the supply voltage which we talked about earlier, uh, that was the to run this IC, and this is the input voltage range to like which you give in the input side of these op amps. Okay, so this is plus minus 13 volts. So this is one more thing. So now large signal voltage gain, okay, you can get till this much gain. This is, now this is also quite interesting to see output voltage swing. So they are saying for like a load, so based on the load resistance, so whatever load you attach at the output of this op amp, that is RL, based on that we that output voltage swing varies. And but the question is, what is this output voltage swing? So let's say I'll tell you like this, where I can get the free space. So let's say here, so you were given, so you gave, let's say, plus 10 volt and minus 10 volt as the main power supplies to this op amp. And at the input you gave here, let's say 10 volt, and this was grounded, and you had some proper feedback. So in order to get this V naught, but if this was the ideal, if this was not the ideal op amp, then what will happen? So let's say you are having RF, R, so this feedback and this input resistance are same R. So according to the formula you will get minus 10 into R by R, so you will get minus 10 volt at the output. But this will not be the case for practical op amps 5, although we gave plus 10 volts minus 10 volts, and we are expecting this plus 10 volts there at the output. But no, because that's what this output voltage swings tells about. Because of these non-idealities, the output will be, so if for the case of, so this plus minus 13 is when we are giving plus minus 15 volt of supply, power supply voltage, it can only give maximum of plus minus 13 volts. So let's say if this was 15 volts, this was minus 15, so if we give some 15 volts, something like that, then it will only output till 13 volts. It cannot output 15 volts exactly, because of this limitation of output voltage swing. Okay, so this is one thing to keep in mind. So they are saying, so supply voltage of plus minus 15 volts, when load resistance is greater than 10 kilo ohm, then we can get plus minus 14 volts at the output maximum. So 1 volt difference is still there. But in case of when we decrease the load resistance, then we get even less, if we get even less output voltage, and output voltage swing increases. So we have plus minus 2 volts of difference here. Okay, so this also you have to keep in mind. So what load resistance you are using at the output of this op amp. This is also fine. Then output short circuit current, they are saying 25 milliampere in order to safeguard your further circuits which you have attached at the output of this op amp. So they are saying, okay, if there is a short circuit current in case, then that will be maximum of 25 milliampere. So you should have accordingly protections in at the output of your op amp. So based on this 25 milliampere thing. Then we have this common mode rejection ratio. This is also very important, although you haven't learned about this, but basically in simple terms, CMRR, we say that as CMRR. So this is common mode rejection ratio, common mode rejection ratio. So this is given by AD by AC. So what is this AD AC? AD is the differential gain of the op amp, and AC is the common mode gain of the op amp, common mode gain. So when you are using an op amp, so let's say I'll again draw something here. So there were two input supplies in an op amp. This was negative, this was positive input, like terminals. So what happens, like when you are giving input, so noise has the tendency to, so you will be having a lot of interferences. So if you are working for like in a frequency range of, let's say, 100 hertz or like 150 hertz, then you can get the noises from this power supplies which are working in India. It's 50 hertz, in outer countries it may be 60 hertz, but they can interfere your signals. So what happens, noise normally have this tendency to to get linked with the both the inputs, like the negative inverting terminal as well as the non-inverting terminals of the op amp. So this is the noise, I will say noise here, also noise. So if you are not giving any signal, but still the noise will be at the both the input terminals, this negative and positive. So it's up to the op amp now how well this op amp can nullify the effect of this signal, this noise signal. So now since the noise is being linked both to both the input, like both the input terminals, that is the inverting terminal of this op amp as well as the non-inverting side of the op amp, that's why this is called as common mode signal. Common mode means common to both the inputs. So normally when we talk about any common mode signal, that are normally noises, because these are being linked to both the input terminals of the op amp. So this AC tells us how well it can amplify this common mode signal, that is the signal which is linked to both the terminals of both the input terminals of the op amp, how well it can amplify that. Okay, that is AC. So ideally we want this to tends to 0. Why? Because we don't want any amplification from noise. We want our op amp not to amplify any noise signal. And what is noise signal? Noise signal is a common mode signal to this op amp. Okay, so we don't want that. That's why we ideally want this AC2 tends to 0. So that means what we want ideally, CMRR to tends to infinity. Okay, because if AC will be 0, then this will tends to infinity. So this is the ideal characteristics of an op amp that we want. But then we miss this AD part. What is AD? AD is basically the differential signal gain. So when we apply some signal, let's say, so normally what we learn in the classes, so we get an output of some amplification based on our feedback multiplied by the difference voltage V1 minus V2. So if this was V1, this was V2. Okay, so we are getting the difference of that. That is the application of this op amp, differential output amplification. So that's what we want, because if you're giving some signal, we want that difference, and that's what this op amps do, and that's our goal also. So that means ideally what we want, ideally we want AD to be infinite. That means it should only amplify the differential mode input, but ideally the op amp should not amplify the common gain. And what is common gain? Common gain is because of the noises. Okay, so ideally we need CMRR to be infinity, but as this is the practical world, we cannot achieve that. But still, we have a very high gain of CMRRs in our op amps. So let's look at what is the CMRR of this op amp. So this is 80 to 95 dB. So dB is basically a scale where we normally, when we talk about common mode rejection ratio in op amps, we talk about this in dB scale, decibel scales. Okay, so if you want to convert this into, so this will be what, so if you want to convert this into like normal scale, so this will be 20 log. So this is the formula for that. AD by AC, that is the CMRR, this is CMRR, equals to 95, let's say 95 dB. So if you solve this, so AD by AC will be what, 95 by 20, so this is the power of 10. Okay, so this was base 10 log. Simply I'm solving this, so this is basically 95 by 20. So that will be, I think, a very high. Let me check. So this will be 10 to the power 95 divided by 20. So it is equal to 56234.13. So like 56, so it is 56,000 something. So that means but we wanted ideally infinite, but we are getting 56,000. But still it is good, but not that good, but still it's fine. We can reject most of the noises. It's still large. Okay, so this was the concept of CMRR. So then yeah, then transient response, if you are like going for, let's say switching circuits, multiplexers, where you have to switch between like signals or something, or like simply if you want to analyze the transient behavior of any signal, then you this rise time and overshoots are important for you. Like if you want to make your signal very fast, and that fast does not mean that to play in milliseconds to like seconds range. It is like even if you have 1 millisecond, now your response time is 1 millisecond. Fast means, let's say you are making it to 1.5 milliseconds. Even that is fast. Also, that is fast. That makes significant difference in your electronic circuitry. In that case, you have to go for this transient response characteristics. Okay, so this is thing. Then slew rate, this is also very important. So this is slew rate, is basically how fast your signal, how fast your op amp is behaving to any input signal. So let's say you gave let's say 1000 hertz frequency of a signal. So if that signal is having a limitation that it can process only up to 500 hertz of frequency. So if you gave, let's say you gave 1000 hertz frequency of signal, this is 1000 hertz, and because of the slew rate limitations, it can only be able to process the signals correctly up to 500 hertz. So what will happen, it will come like this, a triangular wave, the output. So this is our input, 1000 hertz, and it will be output because of the slew rate. Because what will happen, this signal is changing so fast, because 1000 hertz is what, like 1000 oscillations per second. So it is changing so fast that the op amp is not able to uh, cope up with that input. So it is changing like very fastly, so that op amp output is not so it is not that fast. That's why it starts lagging. So that's why we get a triangular or like some skewed waves. So this is also, slew rate is important, that, and its unit is volt per microsecond. Okay, this is its unit. So this is another slew rate. Supply current, okay, this is fine, and the power consumption, that is also fine. So now so whenever you look for any op amp, although every characteristics is important, every parameter, but according, so what I felt very important is that, like CMRR, you should look for this. Then slew rate, you should also look for this. Then offset current and bias current also you should look for. Then then you should look for this offset voltage, that is also very important. And obviously the maximum power supply, voltage supply, you can say voltage supply, which you can give to this op amp. Okay, so these are kind of like these are the things which you should like definitely go into a data sheet. When you look into a data sheet, you should consider these when you are choosing an op amp for your application. And the next important, or I will say among these important thing, is to look for this pin diagram. This is very important. So this will help you in starting with your circuit. If you know what pin is doing, what function, then you can go for that op amp or IC. Okay, so that was the case. So this was for 741A. Yeah, so see, now what I told, why this impracticalities comes. So this is how an op amp looks from inside. So this is like this. So if I give, so whatever there was inside, so this is what inside of an op amp looks like. So we simply show this, all these number of transistors as a triangle, and then we say, okay, this is input side, that is mean V negative, and we have this V plus, and we are getting some V output. Okay, so see, this is output, this is non-inverting input, and then we have this inverting input. But actually this is our op amp. See, so this is our op amp. So lots of things are going inside that. That's why there will be like non-practicalities in this op amp. Okay, so this was like there. So then we talk about this latch up protection. So latch up, like it is basically, latch up is like when you are giving some power supply, and there may be a chance, because since there are so many circuits, so many paths inside an op-amp. So there is a chance so that your power supply may get short with the ground. So in that case, there will be a short circuit and your IC will get damaged. So for that they use this latcher protection thing. Then overload again. They have something for like overload protection also. Then there is pin to pin capability, fine. Now, so now they are telling in this data sheet, so in like lot of data sheets you will get to know about how we can use those op-amps, how we can apply or use that op-amps as for our application. So in this data sheet they have talked about that non-inverting amplifier, but in many of the data sheets you will be able to get more applications of that op-amp, and they have like properly defined like how to connect, what will be the gain, how you can change the gain, how you can remove the offset. All those things are all there in datasheet. So datasheet is very important. So device function modes. So open loop amplifier. So I told you when an amplifier is in open loop, it will act as a comparator. And even if it is in non-inverting, or if the feedback is positive, then also it can act as a comparator. That is, we have talked about Smith triggers in the lecture. So open loop amplifier, they are saying it can be used as open loop configuration. So they are saying the magnitude of the open loop gain is typically large. So important thing is that when we have something like this, there is no feedback to this op amp, then this will be either plus V saturation or it will be minus V saturation, and this is basically plus V supply, this is minus V supply, this is V plus V supply, this is minus V supply. So let's say we gave V1, as I told earlier also we had this V2. So if okay, this is V1, let's say. So if this V1 is greater than V2, then we'll get positive saturation, that is positive V supply, and in the other case we'll get negative supply. Okay, but in order to do this we should have, so in this case we have a gain of this op amp, and that we called as open loop gain, that is AOCL, open loop gain, OL, sorry. And normally this open loop gain, so normally this open loop gain for an op amp should be very high. Okay, so that itself have some like lot of explanation for that, but let's keep it away for that for time being. But we need that open loop gain to be very high. So that's what they are saying. So the magnitude of the open loop gain is typically large, thus for a small difference voltage non-inverting inverting input terminals, the amplifier output will be driven near the supply voltage. That means like for even like this will be, let's say, in millivolt range, the difference between them, then also this output of the op amp will be driven to the like what the near to the supply voltage, that is basically the saturation. And when we are using these as comparators, we want them to drive near to the supply voltages. Okay, so that is a good thing that this op amp, this LM741 is giving that thing to us. Now if we are using this as a closed loop amplifier, then what happens? Closed loop means basically we attach one feedback here that you have already seen, and we have some voltage here. So now the gain of this, so I think if you have done your control systems, so this will be what? Open loop gain divided by 1 plus AOL beta. Beta is the feedback. Beta depends on this, the feedback factor. So you might have seen this thing. So you have, if you have done your control systems, so we have this gain, then we have this output, then we give something as a beta factor, feedback factor, and this was our input, and this is like this is negative. So what is the gain of the system? So G1 plus AG, something like this. Okay, we get V output by V input. So this is the closed loop gain. Okay, and this G is what? Open loop gain. That similar thing which I'm like telling here also. So this AOL is the open loop gain when there was no feedback in this op amp, but when there will be a feedback, then this is the closed loop gain, and this is being controlled by our what, this thing, our RF. So in inverting terminal, what is the feedback gain? That is RF by R1. If this is R1, this is RF. So this is the closed loop gain. In non-inverting amplifier, what is the closed loop gain? That is RF, 1 plus RF by R1. So this is closed loop gain. Closed loop gain for this for inverting amplifier. So you should relate what you have like already read in this lectures and like what is going on here also. So this is non-inverting. So what was that? That was a closed loop gain. Non-inverting amplifier. Okay. So this is a non-inverting amplifier. So we have this closed loop gain, but actually the open loop gain of that amplifier of that op-amp would have been very large. So one reason why we should have this open loop gain to be very high, that you can see here also. So what happens? A equals to AOL 1 plus AOL beta. Now let's say AOL is very high. So what will happen? Let's say we do like this. So this will be we took this AOL common from denominator, and this numerator and denominator AOL will cancel, and this will be looking like something like this. Okay. So if this AOL, the open loop gain of an op-amp, is very high, then what will happen? This will go to zero, because this will be, let's say if it is to infinity, so it will be very negligible, this part. So that means, oh sorry for clumsiness, so that means A will be approximately 1 upon beta. That further means, what it means, like it will not depend on the open loop value. What further it means, like you can control the closed loop gain of this op-amp by just changing the values of these registers, and that is a quite a nice power which came in your hand. So like it's, will it not be very good, like if you can just change vary the resistance values, and then you can get output accordingly without any effect from the internal parameters of that op-amp. I think it's a great power. So that's what this high open loop gain helps us achieving in doing that thing. So that's why this amplifier, this is closed loop gain, close CL I will say. So this is closed loop gain. Okay, so that is how, why we need high open loop gain for this op amps. That is one aspect. Now let's see the application information of this op amp. So you learned about non-inverting amplifier circuit. We saw how we can connect those pins and all. So now they are saying, okay, how we can do this, how we can use this. So they have given an example. If you take some 4.7 kilo of resistor, so normally we use this carbon based resistors. So why 4.7? Because although in theory you can get this 1 2 3 whatever value you want, you can get easily on your theory, but when you go for practical, carbon resistors are having certain values only, so you cannot get each and every value of carbon resistors practically in your laboratories or something. So that those are based on your color coding. So you, if I don't know whether 5k register is available or not, it will be 4.7 or some 5.2 or something like that. That's why they said, based considering the practical aspects, so they said 4.7 kilo ohm is the resistor. You have taken feedback, you have taken here as 4.7 kilo same resistor, so then you will get output. So for output, see they have given the gain also, and that what you have achieved, what you have seen in your classes, in your lecture notes also, 1 plus R2 by R1. Okay, so this is the gain, so you're getting this. So this is so they are saying general purpose that can be used in variety of applications and configurations. One common configuration is non-inverting amplifier. Okay, in this configuration the output signal is in phase with the input, so that you have seen, because the output is what we input into 1 plus R2 by R1. In phase means this is like positive, like this, the sign is positive now. So that's why whatever in output input phase will be, that will be the same phase for the output. That's the meaning of in phase. The input impedance of the amplifier is high, so they are saying the input impedance is high, that because they earlier, if you remember, that was 2 mega ohms input resistance. So if you see, that is like 2 mega ohms, something like this in this case. And the output impedance, so so I think you know this thing. I don't know if you know this. Okay, I will tell you. why we need this input impedance to be high and output impedance to be low, why everyone say always say about that. So when we talk about amplifiers, in case of amplifiers, what happens? So let's say there was a box, let's say this is an amplifier. Okay, we gave some input and we are getting some output. So we say for ideal characteristics of an amplifier, the output impedance should be very low. It should be almost zero and input should be very high. It should be what? It should be infinite or something. So why they say this? Because so when we are inputting something, the goal is, like when we are inputting, the goal is to amplify that signal, and to amplify only that signal, not any other signal. So that's why if we will have some impedance of this, some input impedance of this amplifier, this box, then what will happen? So the, let's say it was having some finite impedance and we wanted to amplify, let's say this was the I1 signal. Okay, and if I open this something, so this was the amplifier. Okay, and this is some circuit and we are getting some output like this. Okay, this is the V output. Let's say this was some finite value, so we will get some drop here because of this finite input resistance. And if we get the drop, so we wanted to measure, so this was our V1 supply, we wanted to amplify this V1 voltage, but instead of that we are basically amplifying the drop after this drop, like the drop after this input impedance of this amplifier. So basically this input impedance of the amplifier is acting as a load to this supply voltage, so it is creating a loading effect. So whatever we wanted to amplify, we are not able to amplify that. But what if like this was very high, so then this would have been an open circuit thing inside that amplifier, and if we are giving some V1 supply, so we will get V1 here also. Okay, and that what we wanted. So that's why we always say when we have in amplifiers, the input impedance should be very high or idealistically it should be infinite. But why we say the output impedance should be very low? Because so whenever we get this V output, so we have this what, how will say that, impedance matching thing. So I think you have heard or not. So let's say this was having very less current or less resistance, that is the output of this amplifier. And if we are connecting further circuit to this, so let's say this was 0 volts or something, like let's say it was 0, this was 0 ohms. So we got this amplification, this I1 current. So we need to achieve this impedance mapping in order, impedance matching. Why? Because otherwise you have must have seen, like I think whether you have read or not. So if we have something, let's say if you are sending some wave, okay, and that I don't know whether you have read this in power systems or not. So whenever you send this wave, so there is some impedance of the receiving end, and there's this which we say as this characteristics impedance. So if this side of that wave and this the receiving end of that signal is not having that same impedance, then because of this there will be some reflection back, so some wave will be going back. So although some will be entering inside, but some will be going back, and that is because of the impedance mismatch of these. So once we achieve this impedance matching, that means this circuit we are having same impedance as that of this circuit, then whatever we are giving, it will be simply going inside that without any like reflection. That is the analogy of waves. I think in 12th we read something about this, but in power systems also we will read about this. But yeah, so we want to achieve this impedance matching. That means the outer circuit should be having the same impedance, or like the similar impedance to like with this thing. So by keeping this output impedance as low as possible, we try to achieve this impedance matching characteristics in case of amplifiers. Okay, so maybe I will give better example next class about this impedance matching. Next class. I'll keep that in mind. Okay, so this is one thing. So where were we? So yeah, we were talking about this. Okay, output impedance is beneficial for applications that require isolation between characteristics of the input and output impedance. Beneficial. Okay, so they are saying because it's isolation between the input and output. Okay, no significant loading will occur. So that's what I said. So loading we should avoid. So by keeping this input impedance high, we will avoid this loading from the previous stage before the amplifier. Okay, the gain of the system is set accordingly to the output signal in a factor larger than input signal. That is fine. Changing the R2 or R1 value, we can achieve the gain. Then design requirements, I told the gain you can solve like this. So one thing to keep in mind, they are saying to use 5% tolerance and you will get 5% tolerance of these resistors, but in order to get better results you can go for 1% tolerance resistance, and that I think you cannot achieve by carbon resistors. You will have to go for SMD resistors. So these are like very small resistors, like very small, and they are used in ICs. And SMD basically means surface mounted devices. So these you can solder using a magnifying glass on like very small device, very small resistors, which provide better tolerance. Like the resistance may vary between plus minus 5%, but there you can achieve 1% and even lesser tolerance in SMD resistors. Okay, and normally in ICs they use SMD, they don't use carbon resistors. Now detailed design procedure. So they said like they will give this supply rails, that is the power supply as plus minus 15 volts. They will use this function generator 1 volt peak to peak, then 10 kilohertz sine wave they are using, and they are using these resistors. Okay, so see, this is how output looks like. So they gave a cost. Basically this is starting from here. So this is, let's say this was cos. Let's see here. Okay, this was non-inverting amplifier. So if we talk about one wave, okay, so one mess, I'll just clearly draw that. So for like this and this, so we have, so let's say this, so we had some signal like this, so it got amplified here. See, earlier we had this much, it got amplified, and but the signal is in phase with the input signal because we had this non-inverting amplifier circuit. And they are saying if you use 4.7 kilo ohm, the theoretical gain of the system is 2, but due to this 5% tolerance, the gain of the system including the tolerance is 1.992. And here you can apply your measurements and error concepts like so 4.7 kilo. So what is the what can be the error in this case? Let's see. Let's apply the theory in this practical aspect. So we have this 1 plus R2 by R1. So what will be the total gain in this case? So it will be, so ideally it should be 2, but instead of 2 what we'll get, so this will be having 5% tolerance, this will be having 5% tolerance. So total tolerance, how much it will be? 10%. Okay, in the final value. So what will be the final value? Since both are 4.7 kilo, so it will be 1 plus minus 10%. Okay, so if we reduce this to, like, let's say 1 plus, so this will be 1 plus minus 10% of that one value. So this is the gain, which we will be getting because of the 5% tolerance in the resistors. So we can get either the gain of 1 plus 1 percentage of 10, that is 1 by 10, or we can get 1 plus 1 minus 1 by 10. So this will be 2.1, or this will be 2 1.9, 1.9 na, 2 minus 0.1, yeah, 1.9. So this will be 1.9. Yeah, so we can get gain either of 2.1 or we can get a gain of 1.9. So this is one more thing. After that, so this is okay, you can do on your own. The gain of the system when measured, so they're saying the gain of the system when measured for the mean amplitude values on the oscilloscope was 1.83. So when they measured this, so they got a gain of 1.83. That is for like further non-linearities, maybe in oscilloscope, or like there can be like lot of non-linearities in this case. So now the next thing, and the next thing is also very important, which I will be going to discuss, that is the power supply recommendations. So when you are attaching your IC, so you had this IC, like let's see, like this, or I will give a 3D view of that. So when you have this IC, so you have these pins here, okay, and similarly at the rear end of that, and let's say this was the notch. So what happens when you are giving the power supply? So in this case of IC, we had that power supply V minus at the fourth pin. So we are, let's say we are giving this to, we are giving some supply here, and the fifth sub and the positive supply, I think it was at the fifth pin. This is the fourth pin. So we are giving some supply here, like this is the power DC supply we are giving. Sorry for Sandy Soda. So this we are giving something like this. Okay. So what happens now? They are saying for proper operation, the power supplies must be properly decoupled. So when you are using, so there can be chance like there can be interference and there can be voltage fluctuations, because this is what this battery is, what this basically a DC amplifier now which you are using in your laboratory. So it can have fluctuation, it can have interferences from power lines, from even from their internal circuitry also. So how to solve that? So in order to do that, to decouple these things, so you have to use this zero point 0.1 microfarad of capacitor. So what you do when you attach these supplies here, so you attach a capacitor here also, and that will be zero point 0.1 microfarad, okay, in parallel to the supply. So what if, like let's say a high frequency signal, like interferences, let's say noise is normally, interferences are normally high frequency, if they come, they will be bypassed from here. Okay, so you will be you will not be having lots of fluctuations in your voltage output. You will not be having that if you are having this ceramic capacitors in parallel with the supply voltage. The next thing is that so one thing, this is recommended, this power supply pins. uh, yeah, and another thing to keep in mind is that, so when you will be attaching these with bias, let's say you use a breadboard and you put that IC inside that breadboard and you are trying to attach these capacitors with the supply in parallel to the supply voltages, then what will happen? You should do that in such a manner that the capacitors are as close as to the IC. So why we want to do that? Because if let's say this capacitor was not here, instead of this it was here, let's say, like just literally I am drawing the distance. So let's say this capacitor was here. So what will happen, because of this wire, this much long wire, although you will say okay this is a very small wire when you will be doing that breadboard connection, but with respect to the electronic circuitry, this will be having some resistance, this may have some inductance, that but you wanted a pure capacitive thing, but instead of that you got some resistance and you got some inductance in your circuit, and that will not give the desired results which you wanted from this capacitor. That means like to decouple, so you won't be able to decouple. So try to attach this capacitor as close to the IC as possible. Okay, so I will write here, uh, try to connect decoupling capacitors as close as possible, as close as possible to this IC slash op-amp, you can say, but it's better to say IC because ICs don't only contain op-amps. They can be switches, they can be like multiplexers, they can be flip-flop, they can be many things. So but since we are dealing with op-amps, so as close as possible to this IC slash op-amp. Okay, this is important. So to avoid these unwanted inductive or resistive paths. So this was power supply recommendations now. So they have given some so when you will be using these when you will be designing your circuits, let's say, so normally you can use Eagle, and Eagle is a software where you can design your PCBs, printed circuit boards, and all the stuff. So I use Eagle. You can use other things also. I think there is I forgot the name of that software. Okay, there is one more software, but I use Eagle. So when you normally try to lay out these, like design these PCBs, so see, this was your IC. So this we say, so when you will be doing these things in your Eagle software or something software which PCBs are designs, so they are like these is called as footprints. So you will be needing footprints like these so when you will send this to for designing or something like that, so these are the solder footprints, so where this copper will be imprinted on that PCB board, so that's why we call them as footprints. So once you get the right footprint for your this IC, based on that, apply that on in this software, and then you have to connect that. So in this case, what they have done, see, take care with lead dress, component placement, and supply decoupling in order to ensure stability. As with most amplifier, take care. So they are talking about for the lead dress, component placements, supply decoupling, that capacitors which we talk about. So in order to ensure the stability of that op-amp, we need to consider these things. So for example, they are saying registers from the output to an input, that R1 register which we talked about, this R1 from the, oh no, so they are saying this is output to an input was the feedback register. I will draw this thing. So this was R1, so this was input pin, this was our supply, because this was like inverting amplifier, non-inverting amplifier, this was V1, this was grounded, this was RF, this was output. So this is output, this is input. Okay, so they are saying register from the input to an input should be placed with the body close to the input. And why it should be? To minimize pickup and maximize the frequency of the feedback pole. So now they are talking about this feedback poles and all those things, that if you want to really deeply analyze what happens if you are if these things happen, these things come into picture, like some resistance or like some unwanted interferences, like how this feedback affects. So I will give you should I give, no, you will get confused, forget about that. But then, okay, so this is like to just keep in mind. So there are in order to maintain the closed loop stability of this circuit, so you will have to keep in mind where the feedback poles lies for and that a closed loop circuit. And if you are like keeping this R2, this was R2, keeping away from that IC, then there may be a chance there can be an there can be a capacitor comes into play, parasitic capacitance. The name of them are unwanted capacitances, are parasitic capacitance. They can come into picture, and that will change the feedback poles positions, and that will lead to instability of this op amps. Okay, in simple words, you can keep this thing in your mind. So but there is still like proper analysis how it is done, what happens when you use that and all those things. But for let's this course, let's keep that aside. So feedback pole by minimizing the capacitance from the input to ground. So they are saying that to minimize the capacitance from input to the ground, that is the parasitic capacitance, they want to do this, keep this R2 as close as possible. Now the feed, as shown in figure 3, the feedback resistors and the decoupling capacitor are located close to the device to ensure maximum stability and noise performance of the system. So this thing you should keep in mind. So this was about them, about this layout. Okay, now the next thing, so then they have this community resources, no need to look into that. So they have this then this is some marketing thing. And so we have this dimensions of that black thing which I showed you. So this L is the loop tube length and W is this all those things, and how it looks like. So see, this is the top view of that IC which I showed you. So this is the side view, these are the 4 pins, and similarly 4 pins are the behind, and these are the the back side of that pin. So this is also fine. So now, yeah, So this is how you should like look into a data sheet of any op-amp. So I think this session may help you like analyzing how you should read a data sheet, how what parameters you should look for in a data sheet, and yeah, the other factors. But this is a very I think a very primitive data sheet. There are data sheets which are in a lot of detail. I'll just give you an example. Let's say LF347. This is a much better quad operation amplifier. So basically it is having four op-amps inside one IC, that black box. So inside that black box there are four op-amps inside that. That's why they said quad. Mm. Okay, so see earlier when we talked, so in this case, see how low this input bias current is. It is in picoamperes, but there in LM741 it was in nanoamperes. So this is much better than that. So it's having very less input bias current. Even they mentioning about this low input noise currents. They are mentioning about this low total harmonic distortions. So gain bandwidth, again, that is a concept in itself. Let's keep it for a while. The high slew rate, it is having 13 volt per milliseconds. I think it's having much better slew rate than LM741. This is also so, and they are telling about the applications. Then see, this was the pin diagram. So now you saw the question that, so the homework for you can be like just read this LF347 data sheet, uh, go through that parameters, like question yourself like what these parameters say, what it signifies, and how we can use that in our practical application when we are using these ICs. And if in doubt, just you can ask in the next session. So these are the different pins, number pins, and then these are the maximum ratings, ESD ratings. See, it is having better ESD rating. There it was plus minus 400 volts, but here it is plus minus 2000, so it's much better. Then we have recommended operating conditions, like in which operating condition you should operate this thing. And again, that same thing, offset voltage, input offset current, bias current, all those things. Now just one thing, CMRR, I will just focus. See, the CMRR in this case is 100, but in the earlier case it was 95 or 90 dB, so it is much better. It is much better than the LM741. Okay, now these are the typical characteristics, but I will be not going into that because we don't have time. And that is, I think, maybe I will give you an example in the next class what these characteristics tell about, but just leave it for the time being. So then they are, see, unity gain amplifier, which I told about, which acts as a buffer. So they have shown that okay, you can realize this with this thing. So this is one application. Again, the complete inside description of that they have given. Then they have used inverting amplifier as an application for this IC, but that is only one application. You can use it for like other applications also. So that is one thing. And then yeah, so this was like when they gave the oscilloscope things and all those, how things look like. So see, they are like telling, we will see how they are dealing with this. So then yeah, so this was then the dimensions of this IC and all. So see, these are having, earlier it was having 8 pins, now these are having 16 pins, 1 2 3 4 5 6 7, and then so 8 here, total 16 pins, 4 op-amps inside this. Okay, so this is like that. So yeah, so this was all about these data sheets. We'll be just fastly we'll go through that data sheet in the next class. Then we'll be solving questions based on the op-amps, so that it can help you in solving like exam related or assignment questions. But yeah, but this was important in order to know about the practical aspects of this op-amp, how to use that based on your applications. So if you have any doubts, you can ask me. You can write in the chat box. Yeah. Otherwise, yeah, I think this much is enough for today. So if you don't have any doubts, then we'll end this session. You can ask those doubts in this discussion forum whenever you want. Okay. So yeah. Okay, I will end this session now. Thank you.